So welcome everyone to our space webinar series, and this is going to be our first. This will start our season 3 of the webinar series. And just a quick note that the actual series has split up into 2 components. One is Space West, and the other is Space East. And this was done to cater to different geographical locations, so we can have attendees from different parts of our planet. So Space West will take place typically once a month, and Space East will also take place once a month, and there'll be space typically 2 weeks apart and take place on Tuesdays. The times will be different. And so to check out the times, please check our Space webinar website, and the times for Space East are posted there. And also there will be a separate registration link for Space East, different from Space West. So this is the Space West webinar series. And for Space East, you would have to register at a separate link that will be posted on our webinar website. That is a quick introduction to changes in our series. And then I would like to introduce the organizers for season 3 for Space West. That's going to be myself, Sai Shankar from Michigan State, and then Jane Zhao from UIUC, Qing, who is going to be our speaker for today. Qing Chu is from U of M, and he's also one of our organizers. And then we also have Katie Bowman from Caltech and Raja Girias. So we are very happy to welcome you to our season 3 of the Space webinar series and to Space West. And for this specific, our first webinar, we'll have one of our organizers, Qing, giving the talk. I would like to give a very brief bio. Qing received his PhD in electrical engineering from Columbia University in 2018, and he received his bachelor's from Tsinghua and master's from Johns Hopkins. And he interned in US Army Research Lab and Microsoft Research in the past, and he's now an assistant professor in the EECS department at the University of Michigan. He was previously a Moore Sloan Data Science Fellow at the Center for Data Science in NYU. And his research interests are in data science, machine learning, optimization, signal and image processing, with a focus on developing algorithms for non-convex problems with convergence and optimality guarantees. And he was also a recipient of a Best Student Paper Award at SPARS 2015 and a recipient of a Microsoft PhD Fellowship in Machine Learning. So with that introduction, I would like to hand the floor to Qing, who is going to talk about from shallow to deep representation learning for imaging and beyond. So Qing, we look forward to your wonderful talk.
Yeah, thanks, Sai, for the great introduction. Hi, my name is Qing. I'm currently a new faculty at the University of Michigan. So in this talk, it's my great pleasure to have some discussion of my recent work on understanding learned representations through non-convex optimization theory. In particular, I'll focus on 2 problems. One is on supervised learning problems, in particular, convolutional dictionary learning. Another is in supervised learning problem, deep neural network training. And we try to understand what kind of representations are learned in deep neural networks. So as a motivation of STAR, so nowadays we are collecting a massive amount of high-dimensional data, increasing in dimension and volume. And we want to utilize machine learning methods to interpret the data. But nowadays, the machine learning methods are critically depending on what kind of representations or features that we use. The performance of machine learning methods is critically depending on the representations that we use. In the past, we used to handcraft features such as wavelets, shift, etc. So nowadays, we are more tend to learn representations directly from the data. On supervised setting, so in a very fundamental problem is dictionary learning problem that we want to learn sparsely utilized user dictionaries from the data. Where the problem is that we have a natural image, and we know that natural image has a lot of redundancies, that we want to represent the image using basic elements such as textures and edges, and we call those kind of basic elements the dictionaries. And for each patch, because we only use very few elements to represent the dictionary, so we want the coefficients to be as sparse as possible. And the dictionary learning problem is that we are given the data as a concatenation of all the patches that we want to learn the compact representation of the dictionary directly from the data. And this often boils down to an optimization problem that we minimize some data fidelity term plus a regularization on the sparse coefficients x. And hopefully by solving this kind of a optimization problem, learning problem, we can learn the representations from the data without label. So moreover, if the data has more structures, say if we want some translation invariance, etc., and we can assume a more structured version of dictionary learning. We can assume our data sample as a superposition of convolutions of convolution dictionaries that convolve with some sparse coefficients. And convolution dictionary learning is that we are given data samples yi, a bunch of data samples yi. We want to learn some convolutional dictionaries and sparse coefficients jointly from the data. And this can be modeled as the translation invariance inside the images. And once we can learn, this can be used for either convolutional or just this kind of a compact representations from data. Actually, we can do many problems in image processing and computer vision, such as image denoising, image restoration, and superillusion, etc. And in supervised setting nowadays, deep learning is transforming every domains, such as computer vision, natural language processing, etc. And vanilla deep networks is that we are given some input x, we are passing through some linear activations, and then followed by a nonlinear activation such as ReLU or max pooling, etc. And recursively until we get the final output. And the deep network is learning a hierarchical representations through the data. And typically in deep network training, so we are given labels. So Y is some labeling, and we are fitting the labels of using the deep networks. And to do this, we also encounter when in the training procedure, we also encounter optimization problems that we minimize data fidelity term plus some weight decay or regularization on the parameters of deep network weights. So, but this all boils down, as we can see that whether we are solving supervised representation learning or unsupervised representation learning, there will need to deal with optimization problem. So the optimization problem that we're dealing with in representation learning is usually much challenging than the simple case, the convex case. Where for convex optimization problem, every local minimizer is a global solution. Then actually, as long as we can find a descent direction, then we can find the global solution efficiently. In contrast, in representation learning, the problem we're dealing with is usually highly non-convex. That if you look at the critical points, the critical points, we can classify them into saddle points, local minimizers, and local maximizers. And for general non-convex problems, we can encounter several difficulties when we're optimizing them. One is that we can encounter bad local minimizers, which are not the global one. So if we just run local search methods, then we might get tracked into the bad local minimizers instead of the global one. So another difficulty is the saddle points. So if the saddle points is extremely flat, then finding a direction to escape the saddle points, we need to compute high order derivatives, which is very expensive. So when we encounter, because this kind of worst case scenarios, in the worst case, when we're solving the worst case non-convex problems, even finding a local minimizer could be an NP-hard problem. But recently, the nice thing that me and my collaborators and other people in the research community find some nice properties of non-convex problems that we study in representation learning is that because the data and the problem itself have some symmetry and intrinsic low-dimensional structures, often we can avoid the optimization landscape we're dealing with is much nicer than the worst case scenarios. Even the problem is non-convex. That what we find is that interesting phenomenon that we find is that the non-convex optimization landscape often has some benign properties. That every local minimizer turns out to be global up to some symmetry ambiguity. And even we encounter saddle points, but actually we can utilize hashing information to escape the saddle point. And because of this, actually we can design efficient global optimization methods to solve the problem to global optimality. And by utilizing this kind of characterizing the non-convex optimization landscapes, in the past several years, we have tackled several fundamental problems in signal processing and machine learning, like phase retrieval problems, low-rank matrix recovery, tensor decomposition, deep linear networks, etc. So if you want to have an overview of this line of work, we have some review papers recently of this line of work. But in this talk, I want to focus on two representation learning problems. One is learning shallow representations, and we'll focus on convolutional dictionary learning problems. We want to understand through characterizing the non-convex landscapes, what kind of representations and how can we learn these kind of representations through non-convex optimization. And secondly, I will discuss a more recent work of understanding what kind of representations are learned in deep neural networks. And we see this kind of representation, we call this kind of representations deep neural clefts. I will explain this neural clefts representation in more detail in my second part of this talk. And the first part of the talk is a little bit technical, and I think the second part could be a little bit more interesting. So please bear me a little bit. So first, we'll discuss a little bit about non-convex optimization for convolution dictionary learning and its application in imaging. So this is based on some recent work, my recent work in iClear last year, that we, through characterizing the non-convex landscapes, that we provide the first global landscape analysis for convolution and overcomplete dictionary learning problems. And we show that by understanding the non-convex landscapes, that we can lead to efficient algorithms with this kind of geometric intuition with applications in imaging. So the problem that we want to solve, as I introduced in the beginning, is this convolutional dictionary learning problem, where the problem is that we are given a bunch of measurements yi, where yi can be written as a superposition of convolutions of some unknown filters with there are some sparse coefficients. And our question is that we are given a bunch of yi's. We want to learn, simultaneously learn the both unknown dictionaries, convolutional dictionaries, and sparse coefficients from the data. And solving this type of problem not only has applications in computer vision and image processing, it also motivates, has many applications in understanding scientific images. For example, this is an image of two-photon calcium imaging in neuroscience. So neuroscientists are recording the 2D images of the brain activities, and they want to know the brain activities, the neurons activities, and they are concatenated by some dendrites. And this image can be modeled as a superposition of convolution of different kernels. One kernel is this kind of neuron kernel. Another type of kernel is the dendrites. And we can see that the image can be viewed as superposition of the kernels convolved with their activation map or their locations. And we want to know the shape of the kernels as well as the locations, and then we can write this problem as a convolution dictionary learning problem. So now our goal is that understand when and why we can solve this convolution dictionary learning problem. But the convolution, here we focus on circular convolution because circular convolution is a little bit simple to analysis. And linear convolution can be written as a linear circular convolution by zero padding. So we focus on this circular convolution. And although this convolution looks a little bit complicated, but actually we can rewrite this in something that we are more familiar with, the matrix form. And we can rewrite this through a circulant matrices because this is a circular convolution. And a circular matrix is a concatenation of all the shapes of the filters. And by utilizing the circular matrix, actually we can write this circular convolution equivalently in the matrices form. And an idea to understand starting this convolution dictionary learning is to relate this problem to the vanilla dictionary learning problem. And through the matrix form, the circular matrices, actually we can rewrite each sample as an overcomplete dictionary, a structured overcomplete dictionary, multiply the sparse coefficients, which is a concatenation of circular matrices of all the xi's. And now we can see that we can write this convolution dictionary in the matrices form. So, and we can relate this convolution dictionary learning problem to the vanilla dictionary learning problem, where the difference is that the dictionary we are dealing with is a structured convolution, a concatenation of structured circular matrices of our unknown filters. So the question is that can we have better understandings of overcomplete dictionary learning first? Because the convolution dictionary can be written as a vanilla dictionary learning problem. So to understand, in the past, our understandings for the overcomplete dictionary learning is still quite limited, although we have a lot of empirical algorithms. So one of the approach to understand dictionary learning is that we try to find one column of the dictionary that we want to learn. The reason that we only focus on finding one column of the dictionary, because if you look at the convolutional dictionary, we can see that each column is basically a shift of the unknown filters, and finding one column of the shifts is sufficient for our problem solution. So our formulation is the following, that we try to minimize or maximize this L4 loss over the sphere. And our hope is that by solving this L4 maximization problem, that the optimal Q that we find can be one column of the dictionary. And the underlying reasoning of why this loss function might be work is that if you assume that X is following some random zero mean distribution, then actually in expectation, this loss function with respect to X is proportional to this inner product between our dictionary and our obtained variable Q. And hopefully, if the dictionary has some structures, then the optimal solution of Q can be the global one column of the dictionary. And in the past, people studied this loss function under the setting where the dictionary is complete, which means that the M is smaller than N, and they assume that each column of the dictionary are orthogonal. And this also relates to fourth order tensor decomposition problems. And people showed that under the orthogonal symmetric setting, then the function, this L4 loss function, actually a strict saddle function with very benign global optimization landscapes. And if you plot the function over in the low dimension, in 3 dimension, that you can see that every local mean matter is just corresponding just to one column of the dictionary. Where the blue color means the function landscape value is more, and the hotter, the warmer color means the function value is larger. And also you can project, this is more 2D visualization, 3D visualization of the function value over the sphere, that you can see that in the orthogonal setting, then every local mean matter of this loss function is just one column of the dictionary. But this kind of orthogonal setting cannot be generalized to the overcomplete setting when M is larger than N. So existing work doesn't generalize to a setting where M is larger than N. So in our work, we generalize this result to where the dictionary can be overcomplete, where M can be larger than N, and the overcompleteness is a constant, and the dictionary is near orthogonal. And what we showed is that in this overcomplete setting, then every column of the dictionary, every local mean matter, global mean matter, local mean matter of this loss function actually is a column of this overcomplete dictionary, and all other critical points are actually strict saddle points that they can be escaped using negative curvature or the Hessian information. And our near orthogonal assumption on the dictionary is often used in study dictionary learning in the past as well, like the tight frame assumption on the dictionary and the incoherence of the columns of the dictionary. And this work provides for overcomplete dictionary learning. Our work provides the first results, a global landscape analysis for the overcomplete dictionary learning, where we showed that for this particular for loss function, every local mean matter actually is corresponding to a column of the dictionary. So now the question pertains is that, so we are dealing with a more structured dictionary learning when we are solving convolution dictionary learning problems, where in the convolution dictionary learning setting, the overcomplete dictionary where each column is a shift of the filters. So can we generalize, so naturally extend the result for overcomplete setting to the more structured convolutional setting, where in general, because the dictionary is much more structured and is not near orthogonal, then the direct generalization doesn't work. So we cannot show a global landscape analysis for convolution setting. Well, to deal with this idea is through preconditioning, that we precondition the data through a preconditioning matrix. And actually this preconditioning matrix makes the effective dictionary we're dealing with is tight frame and satisfies certain properties that we desired for overcomplete dictionary study. And based on this, we can show a local landscape result that we can show that over a certain level set, then the function has a nice local globe over the landscape, the level set, the function has this kind of benign geometric structures. And we can cook up simple initializations to initialize above this kind of local level set and ensure all future iterations stay in the region such that they will converge asymptotically to the global solutions. And we test our methods.
Qing?
Yeah.
I had a quick question.
Yes.
So this optimization would allow you to find a single column of the dictionary each time.
Right.
Correct. And so if you, how would you be able to guarantee with an algorithm that you can find like the k distinct columns? Wouldn't that be heavily dependent on initialization?
Yeah, you need to repeat initializations. You can repeat some random initializations, and each different initialization will hopefully find, maybe you can say log n times, you can find the coupon selection theorem that you can find all the columns at the same time together.
So basically, you would have to run an optimization algorithm many times with different initializations, right, to somehow find distinct solutions.
Yes, that's right. So you can see that in this experiment that we try to learn 3 random filters by the proposed approach, and actually you repeat different initializations that you can learn all the random filters through the optimization. So this is experiment results to demonstrate this. Actually, we can learn all the filters through repetitive random initializations. But Sai asked a great question. So we are only, the theory we showed can only learn 1 filter. So in practically, we want some probes that we can learn multiple filters at the same time. And we find that in practically a more practical formulation is this so-called bilinear lasso formulation if you want to find all filters at the same time. So the reason that we call this bilinear lasso because the filter is also unknown, and we just minimize this lasso loss with respect to A and X and constrain all the filters over the sphere. Actually, we can empirically we can solve this problem to the desired solutions. Although we don't have a theory for this, but the geometric landscape and intuitions actually can help understand why we can optimizing this kind of loss function that we can obtain the global solutions for the filters. The reason is that global solutions are just the shapes of the filters, and the locally the function has very nice properties. And based on this, actually, we can design efficient optimization algorithm to optimize this by linear lasso formulation, such that the alternating descent methods. And by understanding the geometric structure, actually, we can have some algorithm design with extra caveats like smart initialization, homotopy acceleration, etc. Actually, we can, by utilizing the geometric intuition, we can have much faster algorithms and converging to a solution with much higher accuracy, as we show in this figure. And by utilizing the designed algorithm, we can solve many problems in imaging, scientific imaging. One is spec sorting problems in neuroscience. So suppose we are given a time sequence of the data, and we want to jointly estimate, and the time sequence is composed of different type of neurons, and they are spiking at different locations. And this is coming naturally formulated as a convolution dictionary learning problems that we, by utilizing our algorithms, we can automatically estimate the shapes of different neurons, as well as the shapes of different locations, the spiking locations for different neurons. So another application is defect detection in scan tuning microscopy. So this is another scientific imaging understanding problem where, so if you look at this image, it has a lot of defects in this semiconductor materials. And the scientists want to know the locations of those defects. And the image, again, can be modeled as a superposition of convolutions of defects and normal critical lattice kernels convolve with their locations. And by solving the convolution dictionary learning using our approach, we can jointly learn the kernels as well as the activation maps. So this concludes the first part of this talk. In the second part, I will introduce and discuss a more interesting, I think a very interesting phenomenon in deep networks, which is the deep neural class phenomenon for deep learning. And we will utilize similar ideas of non-convex analysis to understand why we can learn this kind of deep neural collapse representation. So this is based on a very recent work where we started as a global landscape of the training loss under a so-called unconstrained feature model that we'll discuss a little bit later. And our results explains why the deep network always learns this kind of neural collapse representations through training. So as I introduced in the very beginning, a deep network is basically, can be written in the following form, where we have an input x, and we are passing input x through weight functions, nonlinear activations, and recursively until we get the output. And to understand what kind of representations that were learned, we focus on classification problems. And say we have k classes, and we consider the classification problem in the supervised setting, where for each class we have different labels, and we utilize one-hot vectors to denote the labels. Say if we have a sample in the S class, then the one-hot vector is basically the label of one-hot vector is basically the ith entry is non-zero, and all the other entries are zero. And the deep network, we're training a deep network for classification. We typically use cross-entropy loss, and we feed the deep neural networks, the output of deep neural networks, to the labels. And we add a weight decay on the network parameters to minimize their energy. We have witnessed tremendous success in classification through deep network training, but there's many mysteries in deep network deep learning, like architectural design, optimization, and properties of learned neural networks, such as generalization and robustness. So, for example, the double descent phenomenon, and overparameterization and memorization, and adversarial attack, etc. But one of the most fundamental problems in deep network is optimization. So why we can optimize deep network to solutions, overparameterize deep network to solutions that generalize well. Because deep networks typically we need to deal with a highly non-convex optimization loss function. And to understand the optimization for deep networks, there are many existing work towards this direction. One is through various simplifications. So one direction is called linear, that people study deep linear networks, but we know that the power of deep networks really comes from the nonlinearity. So this line of work doesn't quite reasonable. So another line of work try to go shallow, that is study shallow deep neural networks. And recent work try to go wide. They study highly overparameterized networks and utilizing the neural tangent kernel technique. But recent work shows that this kind of overparameterization, infinity-wide neural networks, that the neural tangent kernel regime actually enters the lazy training regime that is far from the practical phenomena that we observed in deep networks. So most of the work only answers why we can optimize the training loss to zero, but they hardly provide any insights why the deep network can generalize for practical, especially for practical neural networks. So in this work, we try to go a different approach, that we try to understand what kind of representations or the features are learned through neural networks. Especially we focus on the high level representations, the last layer representations. What kind of last layer representations deep network learning? Are they learning rich and discriminative representations that's such that they can generalize? Well, one of the intriguing phenomena that we find for the last layer representation are the neural collapse representations. I will elaborate this a little bit more detail. So we are focused on understanding the last layer classifier and the last layer features. So if you look at a neural network where the W, the last layer WL, is a last layer linear classifier. And for all the previous layers, we treat them as a feature. So this is a last layer feature. And the neural collapse representation is focusing on the last layer representations of the data. So we are only studying the last layer representation H and W. So, and this is a plot of the last layer representations learned through neural network for 3 classes. So this is an intriguing phenomenon that had recently been discovered by Dave Donahoe and their postdocs. And the phenomenon, and if you look at this figure where each data point is representing the small h, the last layer representation, which is small dots. And this blue, this large blue line is means the class means for each class. And the red one means the last layer classifiers, the W, the columns, the rows of W. So the blue, the red one is denoting the classifiers. So what's happening in deep network training is that in the terminal phase of training, the last layer representations are collapsing. They are collapsing to their class means, and their class means are collapsing to their classifiers, the last layer classifiers. And they are forming a very nice configuration, which is simplex equiangular tight frame, that the features are having maximum margin to each other in the last layer training phase. This is a very intriguing phenomenon, actually happening in a variety of network architectures like ResNet, BGG, etc. And it's happening a lot of different data sets like Cipherton, ImageNet, etc. So this is quite a common phenomenon, prevalent phenomenon in deep network training. And it has very nice and elegant mathematical structures. So mathematically, the neural collapse phenomenon can be mathematically characterized by the following. The first property of neural collapse is that for all the features, so if you consider the case where for each class we have even number of samples, then the features for each class are actually collapsing to their class means. So you can see through this figure that the features are all collapsing to their class means in the terminal phase of training. And the second property is that the class means or the features are having a nice configuration. They are linearly separable and they are forming equiangular tight frame matrix. So basically each class mean to each pair of class mean have equal angle to each other, and they are forming an equiangular tight frame structure. And on the other hand, the third property is that the classifier, the last layer classifier, is converging to the class means. So if you look at the case class, the classifier itself is converging, is collapsing, aligning with the class means. So this is an intriguing, a nice property, interesting phenomenon in the last layer training of neural networks. And basically, what we can find is that in the terminal phase, we are learning the maximum margin classifiers for training samples, for the features and the training samples. So that explains why, this not only explains why the training loss are converging to zero, but actually this reveals what kind of representations we are learning in deep networks. So now the question is that why the deep network are learning this kind of representations? Well, to answer this question, we try to study the optimization landscape of deep network training loss. And here we make quite a strong assumption to study this, where we treat the last layer representation, H, as a free optimization variable. So we treat this as a free optimization variable. Well, arguably, because the feature is from a deep network architecture, it has certain constraints. But here we are treating H as just an optimization variable. And underlying reasoning why we treat H as optimization variable is that the modern deep network are highly over-parameterized, right? So they can almost approximate at any point in the feature space. And because of this, we treat H as a free optimization variable, and we add weight decay or regularizations on both W and H to penalize their energy. And So this kind of free variable assumption of H is called unconstrained feature model because we are not constraining the H via network. And this kind of modeling is also called layer period model, recently studied by Fong et al. But for most of existing work, they studied the different formulations of this loss function, the cross-entropy loss, with regularization, with constraints on W and H. And they only showed that only global solutions are neural collapse properties. But how about other critical points? Also, in practical deep network training, we usually add weight decays instead of regularizations, right? So this kind of formulation are not well aligned with practice. So in this work, we consider this cross-entropy loss plus weight decay instead of regularization. And the result we showed is that for this particular non-convex loss functions with weight decay, the only global solutions are the neural collapse solutions. So the only global solutions are W star and H star that satisfies this neural collapse properties that I elaborated here. And the second property that we showed is that the function doesn't have any bad local minimators. All the local minimators are either global solutions or critical points are either global solutions that are neural collapse, or they are strict saddle functions with negative curvature that can be escaped efficiently. I want to notice that this global solution is only with respect to features. It's not with respect to the network parameters. So when we are considering network parameters, the function could be highly non-convex. It doesn't have this kind of nice properties. So, and our result shows that the deep network always learns the neural collapse features and the classifiers provably. And in contrast to previous approach, yes.
Another quick question. So in your formulation, the H variable is completely free, so it's not dependent on any input signal.
Yes, that's right.
That's a little counterintuitive. I mean, it almost makes it look like some sort of a factorization problem.
Yes, that's right. Yes, that's right. So this is a drawback of our current work. So we cannot study the input, the relationship input. I think this is an interesting direction to study in the future. How can we study the representation to the input, the relationship between the representation and the input. So this is the drawback of the current analysis, limitation of the current analysis. But I want to say that the phenomenon is captures the empirical phenomenon in deep network training, the neural collapse phenomenon. I will demonstrate this through several the experiment results.
Sounds good. Thank you.
Yeah. So the work. So if you look at different previous work in deep network training, understanding deep network training, they take a bottom-up approach, right? They study the network from the input to the output, and they can only often make strong assumptions, and they often can only through study shallow networks, but they don't provide any insights what kind of representations are learned in deep networks. In this work, we study a different approach. We study from the output to the input. It's a top-down study of the features of deep networks. And the difference actually, we can show what kind of representation features, the neural collapse representations through our approach. And this well connects the empirical phenomenon of neural collapse. On the other hand, this also, Sai has raised a very good question, is that this log function is closely related to a low rank matrix factorization problem, right? So if you look at the weight decay of W and H, and the minimization of this actually is minimizing the nuclear norm of W multiply H. So this well connects to low rank matrix factorization problem, right? So we can show actually a lot of the proving techniques are borrowed from non-convex analysis for low rank matrix recovery. So this work well connects to the community of low rank matrix recovery. Although there are some differences to low rank matrix recovery For example, low-rank matrix recovery is a recovery problem. Here we are training a deep neural networks, and the global solutions are different, right? The low-rank matrix recovery have some ground truth solutions, but here the global solutions are neural collapse. Also, the loss function is different, right? We are using cross entropy instead of the least squares loss functions, etc. And finally, I want to show you some interesting experiment results we have that well connects our theory to practice. First of all, our theory shows that the function has global landscapes that as long as we can skip saddle points, then we can converge to a neural collapse solution. And we test this on practical deep neural network architectures on safer data sets with different training algorithms. And actually, we can always observe that our loss functions, we can always observe the convergent solutions neural collapse, where the x-axis denotes the number of training epochs. The y-axis is measuring different aspects of neural collapse, where the first NC1 is measuring the class mean, collapsing to class means, and the NC2 is measuring the configuration of class mean to ETF, and NC3 is measuring the alignment of class mean with the classifiers. So you can see that, so our theory explains that actually by utilizing different training algorithms, actually we can always converge to neural collapse solutions on practical deep network architectures. But although we are always converged to neural collapse, but the generalization performance seems quite different, a little bit different. So this may be that the algorithm has some implicit bias towards different solutions. So another thing is that we're testing neural collapse on random labels. So we have a CBR10 data sets, but the labels are totally random. And what we can see is that when the deep network become more overparameterized, or the Ys becomes larger, then we observe more severe neural collapse solution. So this means that actually the neural collapse is in training is independent of the input. And when you have highly overparameterization, then we have more neural collapse phenomenon. And thirdly, people usually adding weight decay on network parameters, but here we are adding network weight decay on only H and W. So here we test the difference between weight decay on theta and H and W. On practical deep networks, we can see that there's a very slight differences in neural collapse, and the testing accuracy is comparable even we add for different type of weight decays. So even weight decays on W and H, we have achieved on bar performance with weight decay on all the network parameters. So this verifies the model that we studied in theory. So finally, one may ask, what kind of implications that we can have by understanding the representations, the neural collapse representations? Well, here I want to show you that actually by understanding neural collapse, we can improve the efficiency of network training. So here, what we understand is that when the feature dimension is larger than the number of classifiers, and actually the convergent feature classifier are neural collapse, based on understanding of this, so why not we just fix the last layer classifier as a simplex ETF? And actually, we can see, especially for convolutional neural networks, the network parameters are all on the last layer, fully connected layers. And by fixing the last layer classifier, actually we can save quite a lot of parameters for deep network training. On the second hand, we know that the neural collapse happens when D is larger than K, right? So instead of using a large feature dimension in the last layer, so why not we just use the feature dimension equal to the number of classes, right? For CFR10, we can just set the feature dimension equal to 10, and they can save extra parameters when we are training a ResNet and VGG, etc. So this is an illustration that we fix the classifier and making the feature dimension small. And we can see that we can achieve on-bar performance, this almost the same performance with learned classifier and high dimension features for the output. And we can see that by understanding neural clusters, actually we can have improved network efficiency in training and architecture design in training. And hopefully by understanding the learned representations, the neural clusters, we can shed light on generalization, robustness, and transferability of deep networks. This can be future work. So to sum up this talk, so in this talk, we discussed two problems. One is unsupervised shallow learning, convolution dictionary learning problems. Another is neural collapse phenomenon in deep network training. And especially, I would like to point out several interesting directions for the neural collapse work. So here for neural collapse, we only understand the last layer representation and the last layer features, right? So how can we understand the shallow layers, what representation I learn of shallow layers, right? And so hopefully, maybe by existing approach, we can recursively understand what kind of representations are learned through shallow layers. And people, and especially the Verdun, Pierre Pen, has started the shallow layers, the singular values of the shallow layer, features of shallow layers. What they observed is that actually, you can see that from the last layer to the shallow layer, the last several layers have a more severe neural collapse. And for shallow layers, actually the collapsing is much less severe. So how can we understand this kind of representation recursively to the input could be a very interesting direction to be further explored in the future. So another question is that whether this kind of a collapsing phenomenon in deep network training is a blessing or curse. So maybe in natural classification problems, right? The representation, we want the representation to collapse to the class means such that they can have maximal margin. But when we're dealing with unsupervised learning or self-supervised learning or transfer learning, we want to capture the intrinsic structures of data instead of collapsing the data to a single point, because that lose all the information of the data that we cannot do. That's almost impossible to do unsupervised learning or transfer learning. So the fundamental question is that, so can we, if we want to map nonlinear data on nonlinear manifold to linear subspaces, can we design network structures that can preserve the intrinsic data structures, adaptive to the intrinsic data structures through deep network training? So this is a very interesting phenomenon, a question to be further addressed in the future instead of collapsing all the data points to a single direction. So finally, I want to acknowledge all my collaborators for this lab work, and I welcome any questions on this talk. Thank you all.
Thank you, Qing, for the wonderful talk. I think now we have time for a few questions, if there are from the audience. I had maybe a question on, in your simulations or experiments, did you see scenarios where the neural collapse wasn't happening? And if so, what kind of scenarios were they?
So we tried different loss functions. So the neural collapse phenomenon seems, especially in classification, always happening. So we take different regularizations, different loss functions. It seems like the neural collapse phenomenon is prevalent across like cross entropy, MSE loss, etc. And it seems like also in label noise setting that neural collapse, I mean, seems like if you have more neural collapse, you have more benefits in network robustness. So this is a very interesting phenomenon that we don't have fully understanding whether this is a curse or blessing yet. But one phenomenon, one setting that we find that a neural collapse doesn't happen is in adversarial training setting. That in adversarial training setting, it seems like the neural collapse is less severe than the standard training. So this may be that because we want to learn the intrinsic structures of the data such that we can be more robust. So, and in the future, it's a great question to understand whether we want neural collapse or not. So whether neural collapse is a blessing or curse is still not very well understood yet. So in supervised setting, maybe we want neural collapse, but in supervised or transfer learning, because we want to learn the intrinsic structures, in that case, maybe we want to prevent neural collapse.
Mm-hmm. There is a question in the Q&A from anonymous attendee. It is when you fix the last layer classifier as simplex ETF, how to fix it based on input data?
So this is a good question. So actually, we just I mean, here the simplex ETF is up to a rotation, right? U is a rotation matrix. So we can just pick any rotation, random rotation, and fix the last layer classifier as an ETF. And then we learn to the input such that the input, the network learn can adapt to that ETF configuration of the classifier. We can just pick any arbitrary simplex ETF and learn the age through the neural networks. Then actually the network will automatically adapt to the configuration.
Okay, so there was another question by Nicola, and I'm not sure how I would pronounce the last name, so I would just read the question. Was there a relationship between the bilinear lasso formulation and the L4 formulation for convolutional dictionary learning? And also I will enable Nicola to speak if they would like to speak with you, Qing.
Okay. Oh, there's so many.
I think the question is good as stated, but maybe if you answer it and I can ask some further questions.
Oh yeah, so I think maybe I overclaimed my result a little bit. So here we actually don't have a landscape analysis for bilinear lasso formulation. And I think there's no direct, maybe I misinterpreted my result a little bit. So there's no direct relationship between L4 and the bilinear lasso. So, but our intuition is that the bilinear lasso, the global solutions should be the shapes of all the filters. And hopefully some intuitions we can carry the landscape analysis for learning one filters can carry through to the bilinear lasso formulation. But we don't have a precise characterization for the bilinear lasso formulation yet. And empirically, optimizing this bilinear lasso function works wonderfully well. And we don't have a result analysis for this yet.
I think that's all. Thanks.
We have another question from Yoram Bressler. That is, can you elaborate why the intuition from landscape analysis for the smooth L4 sparsity penalty applies to the bilinear lasso, which uses the non-smooth sparsity penalty? And I will also enable Yoram to speak if you like.
Yeah, I think you're asking a similar question. So my answer is that we only have some high-level intuition carried through here that the global solution should be the symmetry solutions of the the filters up to permutation, but the overall landscape analysis doesn't carry through there. So and our intuition, the structure is carried there, but analysis doesn't carry through.
Do you expect that there are any implications of the non-smoothness of the sparsity penalty in this last formulation?
Sorry?
Do you expect that the non-smoothness of the sparsity penalty has any implications on the landscape?
For the let's see. So here we are focusing on A, right? So we are calculating the landscape with respect to A, and if A is if we're only dealing with a single kernel, right? So we're only dealing with a single kernel, then it's Huber loss. When we minimize X, then we marginalize X, and there's a Huber loss with respect to A. So it's a smooth loss function.
Okay.
So with respect to A, it should have some smoothness of the landscape. That is the first order smooth.
Okay. Okay. Thank you.
Okay, I think that's all the questions we have. If anyone else in the audience has questions, please feel free to type it in the Q&A. Or if anyone wants to interact with the speaker, you may post in the Q&A too, so then we can enable your microphone and allow you to speak. Okay, so if there are no further questions, I would like to thank Qing again for his wonderful talk. And just a quick reminder to the audience that the next SPACE webinar would be in the SPACE East series, and that would take place 2 weeks from now on the 21st of September. And it's going to be at a different time that's more suitable for the Eastern Asian or generally the Asian audience. So watch out. The information is posted on our website about the speaker and the talk and the timings, and make sure you register separately for the SPACE East series. And we hope to see you in our next SPACE West webinar, which should be in October. Thank you.